Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.2. The limit of a function.
Lesson 2. One-sided limits.
And here we're going to do some limits. And again, we're going to find the limits from the graph. Let's do the first one together, and then I'm going to have you do parts B and C yourself. So in part A, I'm given a function y equals h of x, and I'm asked to find the limit of h of x as x approaches 2. So I'm going to get closer and closer to this number 2 on the x-axis. Well, if I choose a number that's a little bit less than 2 as an input, say I choose this number 1.8 right here, how do I find the output? I go up to the graph and I go over to the y-axis. And it looks like I get a number that's a little bit above 3. As my inputs get closer to 2, it looks like the outputs are in this case sort of marching downwards towards the number 3. If I choose values that are a little bit larger than 2, say I chose 2.2, I would go up to the black graph, over to the y-axis, and I would get some output value. If I choose 2.1, maybe right here, I go up to the black graph, I go over to the y-axis, and it looks like I hit something that is a little bit closer to 3 on the y-axis. So as these x's get closer to 2, these output values are again getting closer and closer to 3. So what would we say? We'd say the limit as x approaches, but is never quite equal to 2, of h of x, while those output values appear to be approaching 3, and so we say the limit is equal to 3. Okay, I'd like you to go ahead and stop the video and see if you can do parts B and C yourself. Then we'll come back and we'll do them together. Okay, so hopefully you've had a chance to think about those parts B and C. Let's see if we can do them together. Same exact idea. Here I have a new function y equals g of x in part B. Again, I want the limit as x approaches 2 of this function g of x. So I choose values that are a little bit to the left of 2, go up to the graph and over. And the closer I get to 2, the closer these output values on the y-axis seem to be collecting around number 1. Let's be sure that we get the same number on the y-axis if we choose values that are larger than 2. So if I choose a value that's above 2, go up to the black graph and over, I get some value on the y-axis. If I choose something even closer to 2, it does appear as if those values are again marching downwards towards the single number 1 on the y-axis. So whether I approach 2 from the right or the left, through values that are less than 2 or greater than 2, the outputs are collecting around one single number, the number 1, on the y-axis. So we would go ahead and say, yeah, the limit as x approaches 2 of g of x is equal to this number that the y values are collecting around is equal to the number 1. And again, you can put a little not equal sign in there. It's not an official part of our symbol, but it reminds us that x is approaching, but never quite equal to 2. By the way, what would g of 2 be if I tried to plug 2 into this function? Well, if I tried to plug 2 in, I would go right through this hole in the graph and I would hit this black dot, and it looks like I would get an output value of 3. So in parentheses here, I'm just going to remind you that if I found g of 2, I would get a totally different number than the limit. I would get an output value of 3. But again, when we're finding a limit, we only let x get close to, never equal to 2. We're never actually plugging the value 2 into our function. has no bearing at all on the limit. The limit is still equal to 1. All right, let's see if you thought about part C here. I'm asking you to find the limit as x approaches 2 of f of x. And this f of x has kind of a jump in the graph. If you chose values that were less than 2, and up to the black graph and over, you'll hit some y value on the y-axis. And as you choose values that get closer and closer to 2, what happens to these y values? It looks like they're collecting closer and closer to 3. So you might say, the limit must be equal to 3. But what happened when you tried values that were greater than 2? If I choose a value that's to the right of 2, to find the output value, I have to go up to wherever the black graph is. And that's this chunk of the graph up here, and over to the y-axis. And the closer my inputs get to 2, it looks like the outputs are getting closer and closer to the number 5. Remember, for a function to have a limit as x approaches 2, as we get closer and closer to 2 from both sides, the left side and the right side, what has to happen with the y values? We said they have to collect around one single number on the y-axis. Well, do they collect around one single number? Unfortunately, in this case, they don't. They collect around 2 different numbers. As we approach 2 through values that are less than 2, the outputs are collecting around 3. As we approach 2 through values that are greater than 2, the outputs are collecting around a completely different number. They're collecting around 5. So the limit as x approaches, but is never quite equal to 2 of f of x, does not really exist. It's really approaching 2 different values. It has to be approaching the same value as it was in part B and as it was in part A for the limit to exist. And we say it that way. We say the limit as x approaches 2 of f of x, we just say does not exist. Or sometimes, because mathematicians are lazy, we abbreviate it and say does not exist, DNE. We don't say that it's undefined. That's reserved for a function not having an output value assigned to a particular input value. But we use a specific phrase and we just say the limit doesn't exist. There is no one number that the y values are approaching. Now, you might be thinking to yourself, yeah, but as I get close to 2 from the left side, the outputs are collecting around a single number 3. And as I approach from the right side, the outputs are collecting around the single number 5. And can't I indicate that information in some way? And we can. So notice down here I said, however, as x approaches 2 from the left, and that just means through values that are a little bit less than 2, f of x does approach a particular number. We said as we approach 2 from the left, the outputs are getting closer and closer to 3. I'll underline left in red here. So we do say that as we approach from the left, f of x is approaching 3, and we have a way of writing that. We say the limit as x approaches 2, and I want to somehow indicate it's from the left through values that are a little bit less than 2, and the way we do that is we put a minus sign right where an exponent would go. So we say x approaches 2, and this minus sign is read in words, x approaches 2 from the left through values that are slightly less than 2. And we could go ahead and write the limit as x approaches 2 from the left is equal to the number 3. And that is what's referred to as a left-sided limit or a left-hand limit. So even though the function does not have a limit overall as we approach 2 from both directions, we could say that as x approaches 2 from the left, the outputs are getting closer and closer to 3. In other words, the limit as x approaches 2 from the left of f of x is equal to the number 3. and that's referred to as a left-hand limit. Sometimes, just like we write x approaches 2 but is not quite equal to 2, and we put this little not equal to sign into our symbol, I sometimes put a little less than sign here. When x is approaching 2 and we have a minus here, we mean through values x that are a little bit less than the number 2, a little bit to the left of 2. Well, what about as x approaches 2 from the right? What are the f of x values approaching? We said as x approaches 2 and gets closer and closer to 2 through values that are to the right of 2, the outputs are getting closer and closer to the number 5. So we would say as x approaches 2 from the right, f of x is getting closer and closer to the number 5. How do you think we might write that in a symbol? The limit as x approaches 2, and what do you think we might put in the exponent here for values that are a little bit greater than 2? That's right, we put a little plus sign there. So that means x is approaching 2 from the right side through values that are a little bit larger than 2. And what would that limit be equal to? It would be equal to the number 5. Sorry, that's just my slide number down there in the corner. To add to this, the sort of informal symbol here, I sometimes put a little greater than sign underneath my arrow. That reminds me that if x is approaching 2 from the right, it's approaching 2 through values that are a little bit greater than 2. As x is approaching 2 from the left, x is going through values that are a little bit less than 2. For this overall limit to exist, we would be looking at the values as x approaches 2 from both directions. In other words, any values that are not equal to 2. This limit that we just talked about is referred to as a right-handed or right-sided limit, and in this case we would say that the limit from the right of f of x as x approaches 2 is equal to 5. Okay, let's go ahead and look at the next slide. So as I mentioned in words, but we didn't really write it down, we are finding one-sided limits, and I want us to think about the one-sided limits that we looked at earlier. If you think about the last picture that we had a function h of x, and we had a function g of x, and then the last function we looked at was f of x. What I'd like us to do is find the one-sided limits in part A and B for the functions h of x and g of x that we just went over. So let me go back to that slide for a moment. Let's see if we can find the limit from the left of h of x. That means we are only looking at these red input lines here, and notice that as x gets close to 2 from the left, my outputs were getting closer and closer to 3. So if I asked you to find the limit as x approaches 2 from the left of h of x, we would say that that limit is equal to 3. Let's look back at this slide again. I'll try to put it here where you can see it. And find the limit as x approaches 2 from the right. That means I'd be looking at these green inputs, and as x gets closer and closer to 2, but through values that are to the right or a little greater than 2, it looks like the outputs are again collecting around the number 3. So in that picture, we said the limit as x approaches 2 through values that are a little bit greater than 2, a little bit to the right of 2, those values are limiting closer and closer to the number 3. So as x approaches 2 from the left, the limit was 3, and as x approaches 2 from the right, the limit was 3. I want you to think about the limit from the left as x approaches 2 from the left, and as x approaches 2 from the right in the second example, part B, which was the function named g of x, and see if you can find those left-sided limits and right-sided limits for that function. So take a moment, stop the video, and think about that. Okay, let's try that together. Remember that in this second picture, if we get close to 2 from the left, the outputs were getting closer and closer. They were marching down towards the number 1. So the limit from the left would be equal to 1. If we approach 2 from the right, the output values were also getting closer and closer to that number 1. So the limit from the right side is also equal to the number 1. So if I were to write those limits out on this page, I would say that as we approach 2 from the left, in other words through values that are a little bit less than 2, the limiting value is equal to 1. As we let x approach 2 from the right, in other words through values that are a little bit greater than 2, the limiting value of g of x was also equal to 1. The outputs were getting closer and closer to the number 1. Remember that in part A, we said the overall limit as x approaches 2 from both directions, from both the left and the right, was equal to the number 3. And in part B, the limit as x approached 2 from both directions, both the left and the right, was equal to 1. And I want you to think about this question. What has to be true for the overall limit, in other words, as we approach from both directions, to exist? Well, in part A, we saw the limit from both directions was equal to 3, the limit from the left was 3, and the limit from the right was 3. These two things have to agree with each other. They have to be equal. The same thing was true for g of x. The overall limit existed and was equal to 1. The limit from the left was 1, and the limit from the right was 1. These two things agreed with each other. The limit from the left was equal to the limit from the right. So for the limit as x approaches a from both directions of f of x to exist and equal L, that'll be true if and only if the one-sided limits are the same. So it's true if and only if the limit as x approaches a from the left of f of x is equal to some number L, and the limit as x approaches a from the right of f of x is equal to that same number L. In other words, it's true if and only if the two one-sided limits, the limits from the left and the right, exist and are equal. They have to be the same number. In that last example that we looked at, part C, let me put that overhead up again. Remember, we said the overall limit did not exist. Why didn't it exist? The limit from the left existed, the limit from the right existed, but these two one-sided limits were not the same. The limit from the left was 3, while the limit from the right was 5. The outputs were not collecting around a single number, and that's why the overall limit did not exist. For the overall limit to exist, the one-sided limits, the limit from the left and the limit from the right, have to be the same. All right, I want you to go ahead and look at the example that is at the bottom of the next page. So let's go back to this page. And I've got a crazy kind of graph here. This whole graph is the graph of a single function y equals capital F of x. And I'd like you to go ahead and try to find all of these different limits, some of which you notice are limits from the left, some are limits from the right, and some are overall limits. So stop the video and take a moment and try to figure out all of these different limits that are written here. And then we'll go ahead and go through it together. Okay, let's see if we can do this one together. First thing I'm asked to do is find the limit as x approaches 5, and notice the minus sign, so that's from the left. So remember that that means I am looking at values x that are a little bit less than 5, or to the left of 5. If I go over to my graph and I pick an x value that's slightly less than 5, to get the output value, I go up to the graph and go over to the y-axis. The closer my input gets to 5, but always remaining less than or to the left of 5, it looks as if the output values are marching downwards towards the number 4 on the y-axis. And again, don't be confused by this open circle. Remember, we really mean that just a small, infinitesimally small dot is missing from this graph, but it's impossible to draw that on our page, so we draw kind of a big circle here, but really just one tiny, infinitesimally small dot is missing. So it looks like as x approaches 5 from the left, the output values are collecting around the number 4, and we would say the limit from the left of our function is equal to 4. Now let's look at the limit as x approaches 5 from the right. We have a plus sign there. So we are now looking at values that are a little bit greater than 5. So I pick a value that's slightly to the right of 5. I go up to the black graph and go over to the y-axis. And the closer my input gets to 5, staying on the right of 5, it looks as if the outputs are again marching down closer and closer to the number 4. So as I approach 5 from the right, the outputs are approaching the number 4 on the y-axis. And so we would say the limit from the right side is equal to 4. Now what about the limit as x approaches 5? I don't have a plus or minus here. It means it's the overall limit. We are approaching 5 from both directions. We're looking at any x value except for 5 itself. So x is getting closer and closer to 5 from both directions, but never quite equal to 5. And we're just asking, if we approach from both directions, do the one-sided limits agree? In other words, are the y values collecting around one single number on the y-axis? And they are. They're collecting around 4. The limit from the left was 4, the limit from the right was 4, and so the overall limit exists because these two numbers are equal, they agree with each other, and we would say then that the limit from both directions is the number 4. So the limit as x approaches 5 of f of x is equal to 4. Let's try the same thing with x approaching 10 from the left, the right, and then the overall limit. If we approach 10 from the left, it looks like the output values are collecting around, it's a little hard to tell on my graph, but it looks like they are collecting around the number 6, roughly, maybe 6.2, something like that. My graph is not quite perfect, but it looks like the output values are collecting around the number 6. So I would say that the limit as x approaches 10 from the left through values that are a little bit less than 10 would be equal to the number 6. Now what about when x approaches 10 from the right through values that are a little bit larger than 10? The limit as x approaches 10 from the right, in other words, as x gets close to 10 but is slightly greater than 10, it looks like it's a very different number. As I approach 10 from the right, the output values are marching down the y-axis towards the number 2. So the limit as x approaches 10 from the right would be equal to the number 2. What about the overall limit as x approaches 10 from both directions? So x is getting closer and closer to 10 from both the left and the right. Are the y values collecting around some single number on the y-axis? Unfortunately, they are not. They're collecting around two different numbers, 6 from the left, 2 from the right. Or you can just go back up here and say the limit from the left is 6, the limit from the right is 2. For the overall limit to exist, that's true only if the one-sided limits exist and are the same number. These two are not equal to each other. And so we go ahead and say, oh, that means that the overall limit does not exist. And so sometimes we just put does not exist, D and E. And that again is because these two one-sided limits don't agree. Here the limit did exist because the two one-sided limits both existed and agreed with each other. They were both equal to 4. Well, we have 3 more that we're asked to do down here. The limit as x approaches 15 from the left, I go up to the graph and over, it looks like the outputs are approaching, again it's a little hard to tell, but it looks like they are getting closer and closer to the number 6 on the y-axis. So I would go ahead and say the limit as x approaches 15 from the left through values that are a little bit less than 15 is equal to 6. And what did you get for the limit as x approaches 15 from the right? If I plug in a value that's slightly to the right of 15, go over the y-axis, then plug in a value that's even closer to 15, but on the right, it looks as if the outputs are again marching down the y-axis towards the number 6. So I would say the limit as x approaches 15 from the right, in other words through values that are a little bit larger than 15, is equal to the number 6. What about the overall limit as x approaches 15 from both directions? Does that limit exist? Yes, it does, because the limit from the left is 6, the limit from the right is 6. Those two numbers agree, and so the overall limit is equal to 6. Okay, next thing we're going to do is to talk about limits at infinity. Actually, we have one more example before we do that. Let's go ahead and look at these examples on this last page, and then we'll get to those limits at infinity. The example at the top, I don't have a function that is graphed. It's one of these functions that's usually referred to as a piecewise function. It has a different rule depending on the portion of the domain that we are talking about. So in this case, f of x has 2 different definitions depending on what x's we are plugging in. When we are plugging in a value that is greater than or equal to 1 for x, we use this rule, f of x is equal to x plus 2. And when we are plugging in a value that is less than 1 for x, we use an entirely different rule, 3x minus 1. Sometimes we rewrite this whole rule in a little bit different way. We say if x is greater than or equal to 1, then our f of x, or you could even write our y value, is given by this rule, y equals x plus 2. If our x is something less than 1, if our input is smaller than 1, we use an entirely different rule for f of x. We use this bottom rule, and we say that f of x, same thing as y, is equal to 3x minus 1. And sometimes it's easier to rewrite these piecewise functions this way, in a sort of forwards direction, instead of the way that we often write them, which is kind of backwards. Whenever x is greater than or equal to 1, we use this rule, y equals x plus 2. Whenever x is less than 1, we use this rule, y equals 3x minus 1. If you want to sketch the graph, you might go ahead and think about each of these graphs without worrying about these restrictions on the domain, on the x values. For example, if I were to just graph y equal x plus 2, well, what would that look like? It would look like a straight line. This is a linear function. It would have a y-intercept of 2. So if I were just to graph y equal x plus 2 without worrying about the domain of my function at all, I'd go ahead and say, okay, it has a y-intercept of 2, so it crosses the y-axis here, and it has a slope of 1, which we could think of as 1 over 1, rise over run. So remember, to draw a straight line, one way to do it is to draw the y-intercept of 2 and then use the slope. I go up 1, it has a rise of 1, and I go over 1. It has a run of 1. And I would end up with a line that looks something like this. Okay, well that's fine, except that we don't want to have this rule for all values of x. We only use this rule when our input x is something greater than or equal to 1. And so we only want the portion of this line that corresponds to input values that are greater than or equal to 1. So we're only going to look at points that correspond to inputs to the right of 1. That means that if I were just to graph this top line here, I would have to go ahead and say I only want the portion of the line that corresponds to points that's to the right of this input value of 1. And so I actually am just going to erase this portion of the line. We used it to graph the line, but we are only allowing ourselves to plug in x values that are 1, that's this output value, or greater than 1. And so if I plug in values that are to the right of 1, I get these points that are on the right half of the line that I originally drew. And I'll put a little arrow there indicating this goes forever in this direction. Now let's graph the bottom rule, y equals 3x minus 1. Again, if I were to graph it, not worrying at all about the restriction on the domain, I would just say, well, that again is a linear function, so the graph is a straight line. It's y equals 3x minus 1. It has a y-intercept of -1. That would be this point right here on my graph. And it has a slope of 3, which again you could think of as 3 over 1 to think of it as a rise over a run. So I start out at my y-intercept, I do a rise of 3, I go up 3, and I do a run of 1, I go over 1. And I would get a line that looks something like this, crossing right here at -1. Now, if I continued this line, it would go like this. But remember that we only want the portion of the line that consists of points where the input value is less than 1. So I only want to consider the parts of this line that would have x less than 1. And if I choose x slightly less than 1, I would get this point on the line, and that would correspond to all these points that are on the left half of this line. What about right at x equal 1? Remember that we only use this bottom rule when x is strictly less than 1. When x is equal to 1, we use this top rule. So I actually only want the portion of the line that is to the left of this point that I drew right here. I don't want to include this point itself because when x is equal to 1, I'm supposed to use the top rule, and that corresponded to this point right here. So the only way to show that on my graph would be to put a little open circle here on this other half of the line. So just to review, when x is greater than or equal to 1, we use this equation, y equal x plus 2, and so I'm up on this line, and I have a solid dot here because of the equal bar. And when x is less than 1, I use this bottom rule, and so I use this other line, and I only want the portion of the line that corresponds to input values that are less than 1. So only the points whose x coordinates are smaller than 1. And because there's no equal bar here, I have to put an open circle at the end of this little half line, and that again is because we don't want to allow x to equal 1 when we use this bottom rule. So you get a function that looks like this. It's a straight line. It has an open circle on this half of the line, and then suddenly it jumps up and has a closed dot. My pen is having a hard time writing here, and we continue on this part of the line. Now we've graphed the function, and I want you to take a moment to see if you can find the limit as x approaches 1 from the right, the limit as x approaches 1 from the left, and the overall limit as x approaches 1 of this function f of x. So stop the video for a moment and see if you can find those three limits. To find the limit from the right, remember you're looking at values that are greater than 1, and so to get those you'd go through values that are a little bit larger than 1. You go up to the graph that we drew and over to the y-axis. It appears that as I get closer and closer to 1, the outputs are getting closer and closer to 3. We can do it from the graph. You could probably also do it from the equation up here. As x gets closer and closer to 1, something that's closer and closer to 1 plus 2 is getting closer and closer to the number 3. So the limit as x approaches 1 from the right of this function would be equal to 3. If we allow x to approach 1 from the left, well, plugging in a value that's a little bit smaller than 1, I go up to my graph and over. The closer I get to 1 from the left, the closer these output values appear to be getting to the number 2. And so the limit as x approaches 1 from the left through values that are a little bit less than 1 of f of x would be equal to 2. What does that mean about the overall limit as x approaches 1 from both directions? In other words, x is getting closer and closer from both the right and the left, but never quite equal to 1. Does that limit exist? Unfortunately, no. The y values aren't collecting around a single number, or another way of saying that is that the limit from the right is 3, the limit from the left is 2. These two do not agree. They are not equal to each other. And so what do we say about the overall limit? We just say that limit does not exist. All right, I want us to do one last example together. This is kind of a weird function. This is the function sine of pi over x, and it's a very strange function to actually graph. We are going to try to find the limit as x approaches 0 from the right of this function pi over x. Well, one way to do it would be to go ahead and try to graph it just as we did earlier. And maybe to graph it, you start plugging in some values, x, that are getting closer and closer to 0 through values that are a little bit greater than 0, a little bit to the right of 0. So notice here I have an x value of 1, then an x value of a half, then an x value of a third. Those are definitely getting closer and closer to 0, and they're getting closer and closer to 0 through values that are a little bit greater than 0. Let's go ahead and do this both from the table and from the graph and see if we can determine what the limit is. If I were to plug 1 into this function, well, if I want to evaluate this function at 1, I'm just plugging 1 in place of x, so I get sine of pi over 1. That's sine of pi. Remember, pi is the same as 180 degrees, and if you want to, you can think about the unit circle for determining what sine of pi is. Remember, the unit circle is a circle that is centered at the origin and has radius equal to 1. So this point right here would be the point 1, 0 on the right on the x-axis. This would be the point -1, 0. And notice that sine of pi, that sine of 180 degrees, is just the y-coordinate of our point on the unit circle. So sine of pi, sine of 180 degrees, is equal to 0. If I were to draw that point on my graph, 1, 0, when I plug x equal 1 in, I get an output of 0. That would be this point if I were to start to graph this function. If I plug in the value x equals 1/2, I would be doing sine of pi divided by 1/2. If I invert and multiply, that'd be the same as sine of 2 over 1 times pi, or sine of 2 pi. That's the same as sine of 360 degrees. And notice sine of 360 degrees would be an angle that terminates right here. And so I would look again, since I'm doing sine, at the y-coordinate of my point on the unit circle, and sine of 2 pi, sine of 360 degrees, is again equal to 0. So when I plug a half in for x on my graph here, I get an output value of 0. That would be this point on my xy graph. If I plug in a third, I would have sine of pi over 1/3, that would be the same as sine of 3 pi, if I invert and multiply. Sine of 3 pi, I go around one full revolution, 360 degrees, plus an additional 180 degrees, and I'd be back to this same point on the unit circle. Sine of 3 pi is again equal to 0. Notice that as I plug in these different x values that are getting closer and closer to 0 from the right, the output values all seem to be equal to 0. Here was 1/2. When I plug in 1/3, that'd be right about here. The output value is again 0. All of these points are actually right on the x-axis because all of them have y-coordinates of 0. From this scattered information in the table, or this scattered few points that I've plotted, it appears as if when x is approaching 0 from the right, the outputs are all equal to 0. Not only are they approaching 0, not only are they approaching the value 0 on the y-axis, they're all equal to 0. So you might guess, and I'm going to put this down as a guess, you might guess that the value of the limit is 0, that these values are getting closer and closer to the number 0. You might say, oh, well, the limit then, as x approaches 0 from the right, of sine of pi over x, it looks like all the output values are just 0. So they're definitely all collecting around a single value. They're all getting closer and closer to the number 0. However, you can also plot some points that are x values in between these. As an example, you might try the following. So you might go ahead and try a value in between 1 and 1/2. I'm going to try the value 2/3. If I plug 2/3 in for x, I would end up with sine of pi over 2/3. I invert and multiply, I get sine of 3 pi over 2. Sine of 3 pi over 2, that's really sine of 270 degrees. You'd be looking at the y-coordinate of this point on the unit circle. That y-coordinate would actually be equal to -1. So this is sine of 3 pi over 2, turns out to be the number -1. When I plug 2/3 in, let's put it on our graph, that would be right about here, I get an output value of -1. That would be this point right here on the graph. So actually the outputs aren't all equal to 0. This is a function that's kind of curving like this and goes down to a low of -1, and when we get to 1/2, we are back to 0. If you plug something in between 1/2 and 1/3, I chose the value 2/5, you'll get sine of pi divided by 2/5 would be the same as sine of 5 pi over 2, and you can check yourself that that is equal to the number +1. 2/5 is a number between 1/3 and 1/2, so 2/5 is maybe right here. We're at an output value of +1. Remember, sine of any number cannot be larger than 1 or less than -1. So we're getting something that's sort of waving up and down between -1 and 1. And when I get back to 1/3, I'm already back to 0 on my graph. Well, you can continue this process. You might try putting in 2/7. That's a number that's a little bit smaller than the 1/3 that we plugged in earlier. You would end up with sine of pi divided by 2/7, same as sine of 7 pi over 2 when we invert and multiply. And you can check yourself that you again get the value -1. So when I plug in 2/7, which is a little bit smaller than 1/3, I'm down at -1 again. And so my graph is looking something like this. As you plug in values that get closer and closer to 0 from the right, you're going to get a graph that continues to oscillate between the numbers -1 and +1, and it becomes a graph that oscillates between these two extremes more and more quickly the closer we get to 0. So if you continue to plot a few more points in here, I hope you can convince yourself that you get a graph that keeps waving between -1 and +1, but ever more quickly. The closer I get to 0, the faster this oscillates. It's impossible for me to actually graph with a pen that has some real thickness to it, but the graph starts to oscillate more and more wildly. And of course, if I tried to plug 0 itself in, we would get something that's undefined. You'd have sine of pi over 0. Pi over 0 is not defined, so sine of pi over 0 is not defined. So we get a graph that looks a little bit like a regular sine function, but oscillates ever more rapidly as my inputs get closer and closer to 0 from the right. If I were to ask you for the limit as x approaches 0 from the right of this function, you have to ask the same thing that we've asked before, and that is, do the output values collect around a single number on the y-axis as the input values get closer and closer to 0 from the right side? Well, if you wanted a particular output value for this function, for example, if I plug in 1/2, how do I get the output value? Well, that's right on the x-axis. The output value is 0. If I plug in this number 2/3, however, that was right between 1/3 and 1/2, we got an output value of 1. When I plugged in 1/2, I got an output value of 0. When I plug in 2/5, I'm sorry, this 2/3 was an output value of -1. I got that wrong. And the 2/5 was this one. That was between 1/3 and 1/2. I got an output value of 1. The 1/3, I got an output value of 0. And the 2/7, which is a little bit to the left of that, I got an output value of -1. And if I picked other values between the ones that I've chosen here, I would get these other values in between 1 and -1. So the output values, as x is getting closer and closer to 0 from the right, do not collect around one particular number on the y-axis. They actually hit every real number between 1 and -1, and they hit them ever more rapidly the closer my inputs get to 0 from the right. So in answer to the question, do the outputs collect around a single number on the y-axis? No, they don't. They're bounded in value between 1 and -1, but they don't collect around one number. They don't collect around 0 or 1/2 or 1. They keep oscillating and hitting different values between 1 and -1 ever more rapidly as I get closer and closer to 0. So what would we say about the limit as x approaches 0 from the right of sine of pi over x? It's a very bizarre function with a very bizarre graph, and we would have to say that the limit as x approaches 0 from the right of this crazy function does not exist. The outputs do not collect around one single number on the y-axis. They collect around an infinite number of real numbers, all the numbers between -1 and 1. They really don't collect around any number. They just keep oscillating between those values. And so we would say that the limit does not exist. So that's just a really bizarre example, just to show something that's slightly